So this morning we start with Mats van Es from Oxford University, and he will be talking about automatic denoising using ICA for MEG. Mats, thank you for being here, and please go ahead.
Thank you, and good morning, everybody, and especially an early morning for me because it's 8 in the morning in Oxford right now. So indeed, I'm going to talk about automatic denoising using ICA, and I think most of you, everybody who's been using MEG knows that MEG is quite messy, and we always have to clean up the data before we can actually use it. And this can be quite a tedious process because we have to actually look at the data. This is not just something that we can do with one click on the button. So usually one of the steps that we use is ICA, and we use Temporal ICA to decompose our MEG data into a number of components. And I think most people use around 50 to 60 components because that captures most of their the variance in the data. And of those, about 1 to 10% of them are noise. So in general, like in my experience, between maybe 1 and 5 components, I hand label them as noise. But this always has to be hand labeled. And this is a very time-intensive process, and it also requires quite some expertise because you have to be able to recognize different artifacts in the ICA components. So I'll give a few examples of common ICA components. This right here is a clear cardiac component. On the top row, we can see the time course of the component, and there's a big spike about every second or so. On the right bottom, right here, we can see the spatial map of the component, and we can clearly see this dipolar pattern where the poles of the dipole are very far apart. And this indicates that the source is very deep and therefore from the heart. On the left, you can see here the power spectrum, which I generally don't use so much for hand labeling my components, but you could use them as well. And the middle row shows the ECG, which was recorded as well during this experiment. And the ECG, it can be used quite well for automatically recognizing cardiac ICA components. But the issue is that sometimes ECG is not being recorded, or the recording is bad, and then you still have to look at the data automatically, manually yourself. And also recording an ECG on top of your MEG is also a bit of a time investment. You know, you have to prepare the subject with some extra electrodes, and it can also reduce the comfort of the subject, especially if you're maybe recording patient populations. So in the best case scenario, we wouldn't be dependent on extra recordings such as ECG. An extra problem or difficulty is that we can have different sensor types in different MEG systems that have different sensitivity profiles. So for example, if you have a system that contains either magnetometers or axial gradiometers, then the sensitivity is lowest actually right above the source. But for planar gradiometers, the sensitivity is highest right above the source. And that means that the spatial maps that you will see in ICA, they can be very different between different sensor types. That as well, like, requires some expertise to recognize ICA components as artifactual. And it also makes it a bit more difficult if you want to design an algorithm that can automatically label artifactual components. So here's an example of a cardiac component for 3 different sensor types. And you can see that the magnetometers and the axial gradiometers show a dipole, but this dipole can always have a rotation in it. And the planar gradiometers, because we tend to combine the horizontal and vertical components of the planar gradient and retrieve an absolute number, then we don't even have a dipole, but we still see like very heavy weights along the border of the MEG sensor array. Yeah, so a couple of more examples of artifactual components that we tend to remove with ICA, which are ocular components that are caused by the fact that the eyes are also a dipole. So when we blink our eyes or when we make a saccade, we are actually rotating a dipole and disturbing the magnetic field, which will end up in the MEG data as well. And they can be recognized from these high peaks in the time course. And in this case, we're looking at a blink. So we also see this dipolar frontal dipolar pattern in the MEG sensor array. And for a saccade, we would see this big activation or like weights in the frontal sensors as well. So besides the ocular and the cardiac components, there's a couple of more artifactual or like noise components that you could remove with ICA, such as channel noise, line noise, and muscular activity. But depending on the type of experiment you're running, these can usually be easily removed using different pre-processing options. For example, line noise can easily be removed by filtering the data. Channel noise can be removed by just leaving out that one sensor. Muscular activity, especially in a purely visual paradigm, can be removed by just removing the moments in time, the segments of data where there was muscular activity. So therefore, I'm gonna focus on cardiac and ocular components, which are the most tedious ones, and they are always present in the data. So the way I'm trying to automatically remove these or label these components, these artifactual components, is by extending an existing toolbox called Fix, or FIMRIB's ICA-based X noisifier. It's a very pretty name, which was originally designed for fMRI data here in Oxford, part of the FSL toolbox. And this originally used a very complex hierarchical classifier to automatically label ICA components, but nowadays it has been moved to Python, and it has been simplified a little bit, but it's still working very well. And I've been working on extending this toolbox for MEG data. And in order to be able to classify ICA components, I extracted a number of features, a total of 59 features from the ICA components, and these were spatial, temporal, and spectral features. So for spatial so there were like summary statistics like entropy, variance, probability density, and so on. But also some of them were a bit more interpretable, like maybe like features that we would use ourselves when we hand label ICA components. For example, for the spatial components, the single dipole fit. As I said before, like if you look at the spatial pattern of a cardiac component, it indicates a very deep source, and that's what also a single dipole fit would should show you. And then also so for the spectral properties, we have things like power in different frequency bands, and the variance of power in frequency bands, but also like the dominant power, the dominant frequency, I mean, and so on. So in total, we have 59 features that I extracted. And then I use a random forest classifier to classify these components. And the random forest classifier uses a set of decision trees. So we have the data here, and this is one decision tree. And basically, for the decision tree, we just look at our features, and we first pick the one feature that would gain us the most information, and then we just split up the data for that feature and ask, like, if we separate the feature along some border, then we gain the most information about which class each trial belongs to. And in a random forest classifier, we just have a large set of these decision trees, where in each tree we use a subset of the features that are there, and we, in the end, we combine the results from all the decision trees into one class prediction. And we use a random forest classifier specifically because it works well on unbalanced data sets, which is the case in MEG, as we have around maybe like 10% of noise and 90% of signal. It's also robust to outliers and can handle data sets with many variables. And the variables can be categorical, but also numerical. Right, so I've been very lucky to be able to have a great data set to train this model on, which is the MEG UK partnership data. So there's quite a number of MEG machines in the UK, and they partnered up to have this big project where they record many people, like 80 subjects per site, and each of them do the same three tasks, which is resting state eyes open, resting state eyes closed, and the visual motor task. And in total, there's 3 different MEG systems. So currently, I've been working on the data from 2 of those sites, which is Oxford and Cambridge, because when I started on this project, these were already hand labeled, so we already know sort of like maybe like the ground truth. So I should give credit to the people who actually labeled those, because I didn't. So there were other people from my group who did that, which I'm grateful for. So I have 2 times 80 subjects from 2 different sites that both use the same type of MEG scanner. They were doing 3 tasks, and in total, I have about 30,000 components, of which 600 are noise. And now going to the results, and I think the results are really, really cool. So I started out with just like seeing how does the classifier do. So we just kind of try and see like how is the prediction of the classifier versus the ground truth, the hand labeling of the components, with a leave one subject out classification. And I did that separately for the Oxford data and for the Cambridge data. And what you can see here is a confusion matrix that shows, in this case for the Oxford data, of the noise, that is, of the actual noise, 98.3% were also predicted to be noise by the classifier. And of the signal, which is almost 14,000 components, all of them were actually also predicted to be signal. So there's only 7 components out of the more than 14,000 components that were mislabeled, mispredicted, which gives us a true positive rate of 100% and a true negative rate of 98.3%, which is really, really high. If you look into the literature, and there's been other people that try to come up with a classifier or a neural network to or to automatically label ICA components, and generally they do well on the true positive rate. So they are very conservative. They can recognize signal as being signal, but in general their true negative rate is not very high. Or like it's high, but not as high as we would want it to be. It generally is maybe around 80%, sometimes as high as 85 to 90%, but then on a small data set, and it's not known how well they generalize. But this is very high, and in the Cambridge data, leave one subject out classification is very high as well. And then there's a way to look at which features are actually important for this classification, for this performance. And I grouped a number of features together. And this is not just showing, which features are important and which are not, but it's basically how much do you decrease in performance when you remove this feature. And the more to the right that you see it going, so this is for the training data set, and on the right for the testing data set. So the larger this, the more to the right this is going, the more important it is. So if you remove it, then you really decrease in accuracy. And what is quite striking is that these are a few spectral features. So the dominant frequency and the power and variance in frequency bands. It's a very important features, as well as the probability density. But what is actually interesting here is that this large row over here is showing the all spatial features, like the dipole fit, but also, for example, like whether or not the maximum weight is at the border of the sensor array. These don't seem to add anything beyond the other features that we're using here. So it's not saying that these are not important. There might actually be information in them, but there seems to be no unique information in them that we cannot get from the other features. So that's an interesting observation that I might want to look into in the future. But it's actually it could help us, because knowing that we have different MEG sensor types from different mag sites that are mostly different in their spatial maps, and we see here that the spatial maps do not add any unique information for this classifier. It means that we might not be super dependent on these spatial maps, which is a good thing. So it can help us generalize between data sets, and in the ideal scenario, we would in the end have an algorithm, a model that could be used, that is pre-trained, that people can just download and apply to their own data set without needing to worry about like what type of data is it, and so on and so on. So the next step was to see whether or not we can generalize between data sets, which is obviously a prerequisite for being able to work with a pre-trained model. So for this,
Mats, sorry, you have 5 more minutes.
Yeah, okay, thanks. So for this, I either trained the model on the Oxford data set and then tested it on the Cambridge data set, or the other way around. And on the left, you can see the model that was trained on the Oxford data and tested on the Cambridge data. Again, both are both are 80 subjects doing 3 different tasks. And this is actually doing very well. So we see a true positive rate of almost 100%, and a true negative rate of also almost 100%. So there's only in total 12 artifacts are mislabeled, like by the classifier. And for the other way around, when we train on the Cambridge data and test on the Oxford data, we also see a very high performance, which is very promising for being able to generalizing between data sets, and therefore hopefully being able to use a pre-trained model in the future. Then there's one more thing that I checked, because as I said, people were all doing the same 3 tasks in this experiment, and it would not be very good if that creates a bias in the performance of the classifier. Meaning that we have resting state tasks and visual motor tasks, and let's say I have a pre-trained model, but you are doing a visual task, or like a reaching task or something like that. We still want to be able to see a high performance on those tasks as well. So what I did here is I trained on Oxford data and I tested on Cambridge data, or the other way around, but I made a further selection by either training on resting state data and testing on visual motor task data, or the other way around. So that leaves us with 4 sub-analyses. For example, the one on the top left is trained on the Oxford resting state data and tested on the Cambridge visual motor data. So obviously there's less data that goes into training here, but we still see that we have an awesome performance of close to 100%, with the lowest true positive rate, so recognizing signal as being signal, of 99.9%, and the lowest true negative rate, so recognizing noise as being noise, of 95.4%. So this is very promising work, very promising results, and I'm therefore also looking forward to move to the next stage, because now we used only data from the same types of MEG scanners, but really the next step is try to generalize this model to, or like see whether it generalizes to other types of data, especially CTF data. So now we use the Electa data, which contains 2 types of sensors, and if we now can see how well the model does in CTF data, we might have to tweak some features here and there, but hopefully this is looking well. And if that works, then the next step is simply to release a pre-trained model that can be applied to all MEG data, which would then also like save a lot of time and expertise for basically anybody who works with MEG. So I'm at least looking forward to that, and I hope you are as well. Thank you. Yeah, of course, I also want to thank my collaborators here from Oxford, all of them.
Thank you, Mats. Very, very interesting indeed. Very, very, beautiful results. So yeah, look forward to see this, if this can be used a lot. Let me see if there are questions from the audience. We have a question. So the audience can unmute themselves. So if Andreas, if you want to, otherwise I can do it.
Tremendous volume of work. I appreciate how much effort must have gone into doing all these calculations. I have first a simple question. I had a question about whether two systems were the same. You answered that. But in relation to that, did you look separately for the gradiometers and the magnetometers in the ELECTA system? And also, what was the length of the signal that you used in the ICA analysis? Because that would be a very important parameter.
So the first question, sorry, could you repeat?
If you can, okay, the magnetometers and the planar gradiometers are very, very different. So some of the components, though, may give for example, the heart is going to be a very weak component for the planar one, but a very strong one for the magnetometer. So it would be very interesting to see how the ICA can pick that up, and whether or not what are the parameters that this might depend on, because it might give you an idea how to generalize things.
That's very good. Yeah, that's a very good suggestion, actually, which I haven't done. So I have actually combined over these sensors. So I think I've.
Then I have a worry about that, because.
Well, I mean, I have computed the summary statistics separately over both sensor types, but I think I only used one, maybe like the maximum number or maybe the mean of them to as a feature, because otherwise we could run into problems if we have different systems later on. But yeah, it would be good. It would be interesting to see whether maybe like the spatial features are more informative or add more information if we, for example, only use one type of sensor, or if we use them both separately.
That could explain the result in relation to that. But what about the length of the time series that you used? ICA is very sensitive to that. So what did you use? Now, what method of ICA, first of all, and what length of signal?
So this was all done using fast ICA, and I think the tasks were like the resting state was about maybe 6, 7, 8 minutes, something like that, and I think the visual motor task was also around 10 minutes.
So you used for the whole of the signal. You did not chop the signal up.
No.
Then that means that you have to be very conservative in order to get getting the results that you mean. That means a lot of the things that you are cutting down will be signal that you have to cut down because you use a very long process. You don't have the specificity over time. Okay, thank you, but wonderful work anyway.
Thank you.
There's also a question by Victoria. Victoria, please, if you want to unmute yourself.
Yeah, okay. Yeah, I noticed that the rates, the true positive and true negative rates, they differ depending if you train on the CAM dataset and test on the Oxford dataset, or the other way around. And I'm wondering if there's any, if you have any insights, what could be the reason. It would be probably also very informative for the misclassification, like when the model misclassifies.
Yeah, that's a good point. I think what plays a big role, and so as I said, I haven't hand labeled these data myself, but in the Cambridge data there were a lot fewer noise components, about half of them only. So I think there were around 210 noise components in the Cambridge data and around 410 in the Oxford data, which means that if we train on the Cambridge data, we actually have fewer noise components in there, so fewer training examples for the classifier to pick up on. So I think that could play a role here. But yeah, it's interesting to see that it's still doing very well.
Right, thank you.
Okay, thank you very much.